Welcome to EDU World Space.
Chapter 4, number 32, we have a skier being pulled up a 26-degree incline by a tow rope that is parallel to the incline. First up, they want a free body diagram of all the forces acting. We have the weight of the skier, mg, going down. The normal force points normal to the hill. That's why it's called a normal force, perpendicular to the hill. And then we have the tow rope pulling up with tension T. There's no friction on this hill, so we're not going to have a frictional force. So that's the free body diagram. We're good here. Now, for the next part, part B, they want us to calculate the tension in the tow rope if the skier is moving at a constant velocity. So that means that there is no acceleration up or down the slope. So the net force acting parallel to the slope is going to be 0. Now, the trick that I always use when I deal with an inclined plane like this is I rotate my coordinate system so that the x-coordinate, x-axis is parallel to the ramp and the y-axis is perpendicular to the ramp. And what that does is, drawing in our coordinate system here, x and y, now drawing in my mg, my weight force, it's going straight down like that in reference to this new coordinate system. And the reason I rotate the coordinate system is because it's components of the weight force, one of them parallel to the hill and one of them perpendicular to the hill, that affects the motion of these objects. So when I do that, this angle right here is the same angle as the angle of the hill, 26 degrees. And here now we're going to find the two components of the weight force. I've got one component that is going perpendicular to the hill, and I've got another component that is going parallel to the hill. I call these mgy and mgx. You might see them as mg parallel and mg perpendicular, depending on the textbook. But these are the two components we need. Mgy is the component that's equal and opposite to the normal force. Mgx is the component here that's going to be equal and opposite to the tension force. So we are going to need to find mgx here, not mgy. So picking up mgx, putting it down here to complete our right triangle, we see that mgx is the side opposite, and we already know the hypotenuse, that's mg. So opposite and hypotenuse, we're talking about the sine function. So the sine of the angle, which in this case is 26, is equal to the side opposite, that's our mgx, divided by the hypotenuse, that's mg. So mg sine 26, that's the component of gravity going down the hill, counteracting tension. Okay? Always on a hill, your component of gravity going down the hill is going to be mg sine theta, where theta is the angle of the hill. That result is worth memorizing. Mg sine theta going down the hill, mgy is going to be mg cosine theta. That's going to be the normal force on the hill. All right? So going back to Newton's second law, we have the net force in the x direction is equal to 0 because there's no acceleration in the x direction. The force is acting. Tension is going in the positive x direction because remember, I rotated my coordinate system. And we've got mgx going in the negative x direction. Those are equal to 0. So it's clear to see tension equals mgx. And mgx, again, was mg times the sine of 26 degrees. So plugging that into the calculator, mg times the sine of 26, remember the mass of the skier? Sorry, I didn't say that explicitly. 65 kilograms. So 65 times 9.8 times sine 26 is going to give us 279.2. 0.2, how about, newtons. So there you have it. Important results. Mg sine theta is going to be the component of gravity going down the hill. That's why things want to accelerate down the hill. The tension force here is keeping it from accelerating down the hill.